Hello, and welcome to A Gross of Physics. Today is day 131, and what I'd like to do today is discuss different models of the atom. Now, the atom is something that the Greeks thought was the smallest thing that we can have. And the word atom actually means indivisible. So they believed that nothing could be smaller than the atom. Ultimately, we found that we had subatomic particles called the proton, the electron, and the neutron. Now, the different ways to visualize these atomic structures has changed over the years. In fact, one of the earlier models is what we call the plum pudding model. And that was the fact that we had a positive charge throughout the atom with little sprinkles of electrons. So the electrons were these negative charges that existed within what we think of as plum pudding. So it's the raisins in the pudding itself. Now, J.J. Thomson was the one who discovered the electron in 1897, and he was the one who theorized that the electrons were the sprinkles, if you will, in the plum pudding. Now, of course, each scientist would build upon the models that preceded them. So Ernest Rutherford came along, and he wasn't all that convinced that all the positive charge was concentrated or spread throughout. What he believed is that there was a different structure of the atom. And what he ended up doing is what we call the Rutherford gold foil experiment. Now, he took a very small piece of gold foil and he shot it with alpha particles. Now, alpha particles are helium ions. Basically, it's the helium atom with the electrons removed. So when he shot the alpha particles at this gold foil, he wanted to see what would happen on the other side. So he put a collector on the other side to show what particles made it through and how they made it through. And the experiment was something that he wasn't expecting. In fact, he found that most of the alpha particles went right through the gold foil. Now, the alpha particles passed through the solid matter, and he was trying to figure out how that worked. He also found that a number of them were deflected considerably. They bounced off at a very large degree of deflection. Now, because of that, he was able to conclude a few things. First of all, that the atom has a positively charged nucleus, and that all that charge is concentrated in the central location. The reason that works is the fact that since a lot of the alpha particles pass through, and remember, if we have an alpha particle, it's positive. It passed through because most of the atom is empty space. Well, he found that when the alpha particle, which is positive, went near the nucleus, which was also positive, that's when you had repulsion, and it deflected it considerably. In some cases, it bounced right back. So from Rutherford, we figured out that the atom has the positive charges concentrated in one spot, which he called the nucleus, that most of the atom is actually empty space, and he theorized that the electrons orbit this nucleus. The electrons exist outside of the nucleus itself. And we still have that thought today. Of course, there were some limitations to his model. And the fact that electrons orbit like the planets around the sun is something that we don't necessarily believe today. In fact, Niels Bohr came along and he came up with what we call the Bohr model of the atom. And the problem with Rutherford is that it would be that when we have electrons at higher energy levels, if they were just orbiting at any point and they spiraled into the nucleus, that would show light being emitted at every color of the rainbow. Well, as we know, when we look through a diffraction grating at different elements, we don't get a continuous spectrum. In fact, we get what we call the bright line spectra. We get specific spots of color. And that shows that the electrons are jumping discrete values from higher to lower energy levels. Well, Rutherford didn't account for that. In fact, if that were the case, what he predicted, where you had the electrons orbiting around the outside, you wouldn't have a stable atom. They wouldn't exist because the electrons would be pulled in to the atom because of the attractive nature of the positive nucleus and the negative electron, and you would constantly have atoms fall apart. So Rutherford didn't account for the stability of the atom. He was right in the fact that the nucleus was where all the protons were concentrated, but the rest of his model was insufficient. So Bohr came along and he said that electrons exist in these discrete energy levels. And the reason they work that way is they actually produce a standing wave that is stable. As we know, we talked about standing waves with the wave section. And when the electrons are vibrating at certain rates around the nucleus, they are stable. They like to stay in those specific spots. So there are certain parts that are nodal and antinodal, if you will. That accounts for the fact that the electrons can jump to these stable spots, which we call energy levels, and drop back down to different spots when they release their energy. So they gain energy in discrete amounts and they release energy in discrete amounts. And that explains the bright line spectra that we see. The other thing that Bohr's model requires is that you have to have an exact amount of energy in order for the electrons to jump to these higher energy levels, or to release energy in the form of light to jump to lower energy levels. It's similar to staircases. The problem is with a staircase, it's all even steps, unless you maybe built the staircase yourself and you didn't really use a tape measure or something. This is the fact that in order for an electron to jump to a higher stair, if you will, it has to be exact. It doesn't go up higher and then fall back down. You have to have exact amounts. The other thing is the staircase is uneven. Each element has its own set of stairs, and they may not be the same height in each case. So the energy levels allow us to determine what the atom is itself. So we can determine what atom we have based on the light that's released. Now, from the Bohr model, he was able to show the energy levels for hydrogen. And the energy levels for hydrogen are based on an equation 13.6 divided by n squared. And the first energy level, the ground state, is 13.6, and every subsequent level above that is number 2 is 2 squared on the bottom, then 3 squared, then 4 squared, and it works in that way. The problem is hydrogen is the simplest atom. It only has one electron orbiting the nucleus, and it only has a single proton in the nucleus. So it only works for hydrogen in this perfect sense. But we do have an energy level diagram for hydrogen in our reference table, and it lists the energy levels as n equal values, so n equal 1, 2, 3, 4, 5, etc. And the other thing to note is that the energy levels start at the ground state at negative 13.6, and when it's removed from the atom, we call that zero energy. So, for example, if we were to kick an electron with 14 electron volts of energy, well, that would remove it from the atom, which is ionize it. We call that the work function with the photoelectric effect. But then there would be extra energy left over. So that would give it kinetic energy as it was removed from the atom. Within the atom itself, though, it has to be an exact amount that it gains. So the only instance where you can get more energy is if you actually ionize the electron and kick it out of the atom. So for now, that is our discussion of the energy levels. You can look at an energy level diagram for hydrogen in your reference table, and we'll discuss what we can actually do with those energy level diagrams tomorrow. Thank you. All right, what I'd like to do now is just go through a brief history of the atomic models. Originally, we had the Greeks who named the atom, and atom means indivisible. So the ancient Greek philosophers believed that the smallest building block of matter was the atom, and they called it the atom because it means indivisible or unable to be broken in Greek. Fast forward hundreds of years, many centuries later, and we have J.J. Thomson.
And in 1897, he was the one who discovered the electron. And he found that the atom is not the smallest building block. We could actually break it smaller into what we found to be this electron. And we went from an atomic model of just a single building block, that was the Greek atom, to now we have this building block that has smaller things inside, little electrons. And we called it the plum pudding model, basically because you had this mass with electrons sprinkled in, kind of like the raisins in plum pudding. Well, fast forward a little longer, and we move into Ernest Rutherford. And this is in 1909. He did his gold foil experiment. And what he found is that the atom had a nucleus. So we had this nucleus here, and then the electrons were outside the nucleus. So this was our positive nucleus, and the electron was outside. The nucleus was where most of the mass was of the atom. Most of the atom is empty. And that was revolutionary at the time. We're talking about matter being made up of mostly empty space. If we think about it, the nucleus is a very small piece of the atom. The electrons are outside of that, orbiting, and the way they orbit is what's changed over the years in terms of our atomic model. But we have this dense matter that's a small proportion of the entire atom. Of course, atoms are really small, but it's hard to believe that solid objects are made up of mostly empty space. Now, with the Rutherford model, then came the Bohr model. Niels Bohr, in 1913, came up with a model where you had energy levels. And basically, you had the nucleus here, and the electrons were at different orbits, if you will, around the nucleus. Kind of like a solar system type model. And of course, models in science are based on things that people can relate to. It's hard to visualize this subatomic structure, so we tried to visualize it in ways that people were able to understand. Most models in science stem from things in reality that we have a better handle on. So the Bohr model increased the complexity of the atomic structure. Now, if we think about it, we have the Greeks, which was just a single blob. J.J. Thomson put electrons in it. Rutherford separated the electron from the nucleus, which had the positive charge, so all our protons and neutrons. The electrons orbited it. And then we had the Bohr model, which now puts the electrons in specific energy levels where they're stable. If they're not stable, they won't even exist in that spot. Now, of course, electrons don't want to stay in higher energy levels. They release that energy and release it in the form of light. Now, what's really interesting about the Bohr model is that he was able to use an equation to figure out what the value was for the energy levels. And this is what we're going to discuss in our next topic tomorrow. But for the hydrogen atom, we have an equation that can allow us to calculate the energy levels. It's negative 13.6 electron volts over n squared, and n is the energy level. So we have 1 squared, or 2 squared, or 3 squared, or 4 squared, and etc. Now, unfortunately, this equation only really works perfectly for hydrogen because it has the simplest structure. It has a single electron and a single proton. As we get more complexity, this doesn't hold up. Now, every model improves upon the previous ones. And at this point, we're up to what we call the quantum model. And of course, that's being constantly updated as well. But we have quantum numbers. And that was first discussed in the 1920s, around 1927 or so. What that says is that each electron has one of 4 quantum numbers that allows it to have an address, a unique address, almost like a social security number would be for us today. Each person has their own unique identifier. So the electrons have 4 numbers that represent them. We have the principal energy level, we have the angular momentum, we have the magnetic property, and the magnetic spin. And the spin can be either positive or negative. The magnetic properties can be different, and each electron can have a specific number. Angular momentum has a specific value, and the one value that continued from the Bohr model is the principal energy level. And what this is doing is allowing us to further understand the atom and make it more applicable for more complex structures. Now, in this course, the quantum model is not something we cover too in depth, but I want you to be aware of the fact that the quantum model exists. In order to identify an electron, we use 4 numbers, the N, the L, the M sub L, and M sub S, and each electron in an atom will have a unique set of numbers. Each one of these improves upon the previous one. We go from the Greeks to J.J. Thomson in 1897, and if we look, within 30 years, we have a much better understanding of the atom and the atomic structure. We're still understanding the atom better today, and we're finding that the subatomic particles, the proton, the neutron, and the electron, are not the smallest building blocks of matter. In fact, it's made up of even smaller things that we call the quark. And we'll discuss that in a later day. But for today, here's the atomic model and a brief outline of the history from the Greeks up to the quantum model.